All right. So we're starting to move into more rational functions. We're going to look at long division, synthetic division today. But we're going to start off, we've ended last class doing some domain and range. Start off this class doing a little bit of domain and range. And we're going to do a couple inequality problems, which some people might not remember how to do. So we're going to do those couple first, and then we'll move into the long division and factor rules. So if we're looking at the domain for this function, what are the things that would restrict the domain? What's 0? The denominator is 0. So I'm basically going to look at that x squared plus 16x plus 64. So I'm looking for ones that does not equal 0. Okay, so we have to factor this. So two numbers that multiply to 64 and add to 16. Yes. Yeah, in this case, it's 8 and 8. So we've got x plus 8. X plus 8 does not equal 0. So in this case, the only one that doesn't work is negative 8. So my domain for f of x, since this wants it in interval notation, I have to do so negative infinity to negative 8, and then the union of negative 8 to infinity. So that's how that would be written. Notice that they're all parentheses because you cannot include the infinities, and we don't want to include the negative 8. All right, so let's look at the next one. Same concept. We're just looking at the bottom. So x squared minus x minus 30 does not equal 0. So what are the two numbers that multiply to negative 30 and add to negative 1? 5 and negative 6. So x plus 5 and x minus 6. So I have x does not equal negative 5 and x does not equal 6. Does it matter that the x plus 5 is already on the top there? Does that change my domain at all? No. It will change what the graph looks like. So at x equals negative 5, there will be a hole in the graph, not an asymptote. At x equals 6, there'd be an asymptote. So it will change how the problem looks, but it does not change my domain. Negative 5 still does not work in it, even though it is in the numerator. So in this case, we're going to have a little bit of a longer list of my domain. So I got to go from negative infinity to negative 5, and then from negative 5 to 6, and then from 6 to infinity. Again, notice that they're all parentheses because I do not want to include those. If I'm talking a little louder, I'm sorry. My ears are still ringing. I really shouldn't have stood next to the stage.
All that screaming.
Yeah, it was a little loud. Music. So, this is saying before, I'm getting a little old for this, but it's so much fun, so I can't complain. All right, let's look at the next one. So the next two topics are similar to domain and range. It's looking at the values, that, the actual answer, and it's using a number line to graph it. So this is looking at quadratics, inequalities. So when you're looking at a linear inequality, they're pretty simple and straightforward. As long as they're greater than or equal to, it's pretty much it. You just put your point there and draw your line. However, in quadratics, it become a little more complicated because we have multiple values that they work. So we have to figure out where my line is going to be because it can be in multiple places. So when we're doing a quadratic inequality, the first thing we want to do is to find the endpoints. So basically exactly what we just did a minute ago, except this is not domain. We're looking for where they equal 0. So this one is in factored form, so it's easy for me. I have x equals 0 and x equals 7 are my two 0 points. Any question on where I came up with those? Should be pretty simple. All right. At those points, am I going to put an open circle or a closed circle? Yeah. Why open? The key is right here. It doesn't equal it. If there's that little line underneath it, closed dot. No line, open dot. In this case, I'm going to have an open dot at 0 and an open dot at 7. So now what I need to do is I need to test each of the locations. So I'm going to pick a number on this side over here. So let's take -1. Pick a number here, we'll take 3, and pick a number here, we'll take 10. And I just got to test it to see if it's greater than 0 or not. So if I have -1 minus 7, so I get -1 times -8, which is 8. Is 8 greater than 0? Yes, so that side's shaded. Check the 3. 3 minus 7. 3, -4, -12. Is that greater than 0?
No.
No, so I don't shade that part. And then the 10. 10 times 3 is 30. 30 greater than 0? Yes, so I shade that part there. Now, in most situations, you're going to have one of two cases. You're either going to have the lines going out like I have here, or the lines between the 2 points. Okay? In most situations. There are some situations where it comes in where the entire line shaded, or nothing shaded. Those can happen, rarely. So if I got the -1 and I know that side shaded, you pretty much can be assured that the other side's going to be shaded, right, and not the middle. But like I said, there's always those rare situations that can happen. So, all right. Now, when we're graphing this one, I want to show you this one so you can see how it's graphed. So we just going to take the points, put them on the dots. In this case, it was 0 and 7. And you just click the lines where you're going to click where you want them, and it puts the lines and the arrows there. All right. Put this one. All right. To do this one, how do we start with this one? Yeah. Yeah. You always want your quadratics equal to 0. Could you solve it for a -8? Yeah, but you're going to have a lot of different values that could possibly work. Where 0 makes our life easy. One of them has to be 0. So we're going to move that -8 over. So x squared minus 6x plus 8 is greater than 0. So now I'm looking for two numbers that multiply to 8 and add to -6. And -4 and -2. So I have x equals 4 and x equals 2. So if we do my quick little number line, open dot or closed dot on these? Open, because again, not there. So we're going to pick a number here. There's only 3 here. We'll pick 5. And if you can choose 0, choose 0. 0 is always there. Yes. Yeah, you can choose any number on that interval. It doesn't make a difference. As long as it's not 2 or 4, it doesn't make a difference which number you choose. So I could have chosen 1, 3, and 5. It would be fine. You could technically have chosen like 2.5 and things like that in there if you wanted to. I don't know why you would want to, but you could. So yeah, any of the numbers would have worked. Now, my suggestion when you're doing this is always go back to the original problem. Okay? So don't work with your factored form. Go back to my original problem and work with that one. Yes, it might be a little harder to do. However, if you screwed up over here, it will help you figure that out in here. So remember I said normally it's either outwards or inwards in between the two. So like if you plug them back in here and you get something crazy where like the entire thing's filled or nothing's filled, you might want to go back and look at your work because you might have messed up the factoring piece. So it's that extra piece of check that you do there. So we're going to go back up into the original problem. So I have got 0 minus 0 is greater than -8. 0 is not greater than -8. So that side I'm not shading. Oh, you're right. 0 is greater than -8. Sorry. So yeah, I'm going to shade that section there. Yeah.
When you solve it, it was positive, they solve it like how you did it.
Oh, if you use this one?
Yeah.
You could use that one. Yeah, like I said, it's like you can use any of them. You could have used the factored form for it too if you wanted to. The key piece there is that it's just one of those things like the more steps that you have done when you're trying to check work, the more likely that if you made a mistake, you're not going to catch it. So you kind of want to make sure that you try your best not to use things that you might have messed up. Or like me, just forget that 0 is greater than -8. All right. If you did this one, yeah, you'd have had 8 is greater than 0, which is true. Yeah, 8 is greater than 0. So yeah, it still would have worked. The answer should come out to be the same no matter what. Like if you did here, if you plugged it in here, you'd got -4 times -2, which is 8 is greater than 0. So that still would have worked. And it works because we know we did that part correct. All right, so let's try the 3. So I've got 9 minus 18. So -9 is greater than -8. My vast wisdom, I'm going to go with that's not true today. All right, and then we'll try the 5. So we got 25 minus 30 is greater than -8. And -5 is greater than -8. That is true. So we're going to shade that side. And that's what I would expect my graph to come out to be. So I'm probably right. If I would have said, oh, I screwed that one up and said, okay, 0 is not greater than -8 like I did, I wouldn't have gotten that one shaded. This one wouldn't have been shaded, but this one would have been shaded. And then I would have gone back like, wait, something's wrong here. I probably should have had something else shaded here. And then I would caught my mistake. So those are when you're going through your work, using multiple ways to check your work is always very helpful. So you don't mess up and Alex gives you more topics to do. All right. Any other questions with inequality graphing? That's pretty straightforward. And if we're going to do it on a graph, it'd be the same concept. You just pick a point and check the thing to do your actual graph piece there too. All right. Let's do do not use your calculator and do this problem. See how much you remember in elementary school. Because it's probably the last time you did long division. Unless your college algebra professor did it. Oh, you just have to go. I'm literally like I'm looking at different methods people are using to do it on purpose. Like see. Huh? Yeah. I'm gonna show you a. It does keep going. No, you're fine. I was over here. I'm looking at methods. I know it's been a while, but you guys have probably done this stuff. It's fine. For the remainder of three. All right. The reason I do this problem before that problem is it's actually the same method. One of those things that when you're in elementary and middle school, your teachers will sit there and teach this to you. And then at some point, a professor or a math teacher will go, you don't need to do that, just use a calculator. And that's true. However, that method is used in algebra and pre-calculus and calculus and stuff as well. So understanding that method is important. Problem is that most people don't ever get that level, so you don't end up using it again. So let's go through this. First step, you want to look at how many times the 6 goes into the 7. You're doing it piece by piece. So in this case, that's once. Then you multiply and subtract. So 1 times 6 is 6. We're subtracting. And then you bring down your next number. 6 goes into 13 twice. Multiply. 6 times 2 is 12. Subtract. Bring down. 6 goes into 12. 2 times. 6 times 12, or 6 times 2 is 12. Subtract. Bring down. 6 goes into 5. 0 times. So in this case, my remainder is 5. So you might have seen this. Now, this is where I saw a lot of variety going around. Most people kept going and going into decimals, okay, which is fine. There's actually a few different ways you can write it. When we're dealing with the algebra, you're stopping there. We can't keep going. So there is no decimal answer. What you'd want to write it as is you'd actually want to write it as a fraction. So this answer is 1220, and then it's 5 over 6. So that's how you'd write. You write it as a fraction. All right. So now let's look at the algebra one. We're literally going to use the same methods. The only thing is we're only looking at one number. So we're only looking at one piece of information. We're looking at that x. We're looking at the very first piece. So how many times does that x go into x squared? Twice. Well, not twice. So okay. Let me yeah. Let me do this let me actually say this a different way. What is x squared divided by x? X. Because the goal is I want to get rid of that piece in the beginning. Okay. So what do I got to multiply x by to get x squared, or what is x squared divided by x? So x. So x. Notice I'm not putting it over the x squared. There's a variety of different methods that teachers use and the books use. So sometimes they'll put it right over the x squared. That's fine. I like keeping everything lined up. So since it's an x, I'm putting it over the x term. Okay. This also helps at the end because when you get to the very end, you know you're done because there's nowhere else to put something. Okay, so that's helpful there too. So now I'm going to do the same thing. What's x times x? X squared. What's x times negative 6? Negative 6x. Notice how everything lines up. You want the stuff to line up. This means if you're missing something, you have to put a 0 or something in there to keep a placeholder. Just like if I'm writing 1,003, I don't write a 1 and a 3. I put a couple zeros between there. Same concept here. If I was missing a term, I'd put a 0 in there. We will do a few like that. Don't worry. All right. So now I'm going to subtract So that means when I'm subtracting, I change the signs of both pieces. And then I come down. So x squared minus x squared is 0. That should always happen. If that first term does not disappear, you made a mistake. What's negative 13x plus 6x? Negative 7x. And then I bring down the next terms. Now, we're looking at that goes into in the negative 7x. So what do I got to multiply x by to get negative 7x? Negative 7. So that's negative 7. Now we do this process again. Multiply, subtract. Negative 7 times x, negative 7x. Again, those two should be identical. If they're not, you know you made a mistake. Negative 7 times negative 6, positive 42. Again, change my signs. First terms cancel out. Negative 7x plus 7x. 39 minus 42 is negative 3. So my answer, I think the way they want you to write this one, if I remember right, was this one they asked for the remainder. So this one is x minus 7 with a remainder of negative 3.
So how would you think that?
I'm going to show you. Because Alex asks for it in a few different ways. Before I switch over to Alex, questions on the process there? Do you see the connection between the two sides? It's very similar in the process. Okay. This one's a pretty simple case with just the x minus 6. We will get into more complicated cases where there are a little more work involved in them. All right, so let me share this. So Alex asks for these questions in a few different ways. This one wants the quotient, wants the remainder as two separate answers. So in this case, my quotient would be, was it x minus 7? And my remainder was negative 3. Okay, so in this case, that's the way Alex wants you to write it in. Which is why I'm showing this now, because if you don't put it the way they want it, you don't get the right answer. And
I kept putting it over like
yeah,
the
the x minus 6.
Yeah.
So I said, and there is topics in Alex that they want that written there. So it's like you have to give it to them the way they want it in this case. So, all right. Okay, we can see this one. Same concept. They want the quotient and the remainder. So let's work on that. Let's do this one. Yes. The first one, the one we just did, yes. This one, no. I actually am going to do synthetic division. I'm going to show you which ones. Yeah. So synthetic division works only when it's a linear term. Anytime it's not a linear term, you can't. So actually, technically, this one you actually could do a synthetic division. You'd have to do it twice. Because you'd have to factor the 2x squared plus x and do them as two separate problems, and actually probably be more complicated in that situation. But typically when you're doing synthetic division, it's just a linear term. You're thinking of something else.
U over Q and then you find a 0.
Oh, that's just rational functions. You're looking, that's finding zeros for rational functions. We will do that. You do use long division to do that, yes. All right, so let's look at this one. So we're going to set it up. So 2x squared plus x was on the outside. The nice thing is nothing is missing in this one. So I don't have to add a 0 in there for this one. But let's say, for example, that 7x was missing. I would have put a 0x there. Okay, fill in the holes. Always want to make sure you have all your terms. All right, same concept as before. We're looking for or a number or something, or when I divide 8x to the third divided by 2x squared, what do I get? I get 4x. And notice I'm going to put it over the 4x. Now, let's multiply. So 4x times 2x squared, it should give you 8x to the third. If it doesn't, you made a mistake. 4x times x is 4x squared. Change my signs. Subtract that. You can bring everything down. You don't necessarily have to. In some situations, especially when they're not a linear term, you can't, like, you might have to use multiple pieces of it. So that can come into play. So a lot of times in these more complicated ones, I'll just bring everything down. Now we're looking at the 2x squared going into negative 2x squared. Goes in negative 1 times, so negative 1. Negative 1 times that is negative 2x squared. Negative 1 times x is negative x. Change my signs. Negative 2x squared plus 2x squared is 0. 7x plus x is 8x plus 2. Now, this is why I typically write them as they're coming over each other. Sometimes you'll look at this and go, okay, I can keep going. I still have an x left. There's nowhere to put it. So I know I'm done. The other thing you want to look at is there's nothing 8x divided by 2x squared is going to give me a negative exponent. Okay? Which I also don't want. So, but that's why I typically write them so that that goes to there, because when I'm at the end of my division set, I'm done. So it just gives me another visual reminder that I'm done with this one. And this one, that's your quotient, and that's your remainder. So your remainder can have x's in it. That's possible. All right, especially when you're not dealing with a linear divisor. I know. I needed the the answer. All right, so we type it in there. Notice my remainder has the x in it. Again, no division. You can't actually, if you try to do the division, it won't let you.
Have you already read it x squared?
Yeah, so if you're doing this as a fraction, you write the 2x squared. You always write your divisor as the denominator. I think this is the one that, yeah. So this is the other way that they can have you write it. This one, notice they already have the fraction in there for you. So in essence, all again you're doing is you're writing your quotient and your remainder. They already have it set up for you. It's actually no different than the last problem. They just have it written out differently. So they're doing it this way so you don't have to do the division sign and put the quotient underneath. They've already given it to you. So, all right. Put this one over there because I'm going to have you guys actually try this one. All right. Try this one. Yes, there's a few things that this one has in it that's gonna might trip you up. I was waiting for that. Keep that on track. Yeah. All right, a couple things on this one that some people caught, some people didn't. This is literally why this one exists. They're long, yes. That it is in the title of the actual topic, long division. They're not in order. You need to have your or quotient in order, or your dividend in order. You also don't have the x term, so you want to put a 0x in there. Do you have to do either of those? No. It just makes your life a lot easier. All right. So when I wrote this one out, it'd be negative x squared plus x plus 3. And then I'd have negative 7x to the fourth. When you're moving things around, make sure you keep the sign that's in front of it. Nice thing in this one, they're all pluses. That's not always the case, though. So I have plus 5x to the third plus 20x squared. I'm missing my x term, so I'm going to put 0x there, plus 10. Again, you don't have to. Again, it's a quality of life thing. It makes your life a little easier when you're going through and doing it. Less likely to make a mistake, less likely to miss something. All right, so now we can divide these. Again, we're only looking, when we're doing the division, at the very first part. So negative 7x to the fourth divided by negative x squared is what? So it's 7x squared. So I put 7x squared there. I multiply. I get negative 7x to the fourth. I get 7x to the third and 21x squared. Yes. Oh, you're right, I did. Good catch. All right, so now we're going to change my signs. So plus, minus, minus. Negative 7x to the fourth plus 7x to the fourth cancels each other out. 5x to the third minus 7x to the third is negative 2x to the third. And then 20x squared minus 21x squared is negative x squared plus 0x plus 10. Next step, negative x squared goes into negative 2x to the third. We have negative 2x, or no, positive 2x. Now, if you didn't have the 0x in there, you'd have a 2x and nowhere really to write it. So you'd probably try to cram it in between the two pieces, and it just makes it a little messier. Multiply, so negative 2x to the third. 2x squared plus 6x. And then you'd have a 6x down here that you wouldn't have necessarily had somewhere to put. So change my signs. And subtract or add. Negative 2x squared to the third plus 2x to the third is gone. Negative x squared minus 2x squared is negative 3x squared. 0x minus 6x is negative 6x. And bring down the 10. I still have a spot, so I'm not done yet. So this is going to be a 3, so plus 3. And we have negative 3x squared plus 3x plus 9. Change sign. So that's my quotient, and that's my remainder. Now, depending on how far you're going in math, you don't typically end up doing long division again until Calc 2, which and then your teacher will end up reteaching it to you because you'll have forgotten by then. All the times I've taught Calc 2, I've had to literally do that again because nobody remembers how to do it. So actually, the first chapter in my Calc 2 book that we just wrote had all the parts that I normally have to reteach for Calc 2, and this was one of the sections in it because people just don't remember how to do it. So don't feel bad if you don't remember how to do it at this point. It is one of those things that most people don't do on a regular basis. So, and they're really, honestly, for anything other than a linear quotient, there is not an easier way to do it. The linear quotients, I'm going to show you synthetic division, which makes your life a little bit easier. And it'll help us out when we start to do some of the factor and remainder theorems. Let's put this answer in. I know you can't see, I'm using it to type, and then I'll switch over before I hit enter.
How fast would you give us a question that's that long?
So when I'm designing my tests, it's funny. I used to design them so that it would take you guys about twice as long as me. I'm now up to about 4 times. So I'll design the test, I'll take it, and if it takes me about 20 minutes to do, you should be able to finish it in an hour and 15. So that's about how I figured it out. So yes, because I know how to do it, so I should be able to do it faster. But also, I literally write out and do the whole test out by hand, just like you guys would. So actually writing out problems and stuff like this, if it's taking a while, then that's going to count into that piece there too. So will I have one maybe this long on there? Probably not. I'm looking for if I'm going to test your long division ability, I'll probably do a topic like the one before this one, just because it was a little shorter, but it still gets to the same concept. So yes. So because it's on paper, I'll give you partial credit because I'm going to see all your work right now. So when I used to do it on Alex, I would give you a second attempt because I didn't check your partial credit. So, but since it's on paper, yes, I'll give you partial credit. So it does help you to show you all your work when you're doing it.
Nice, so you partial credit.
I'm pretty easy. I'm pretty good at it. Because again, I'm looking for when I'm giving you a test, or when any teacher that is supposed to be when they're giving you a test is, our goal is to figure out what you know and what you don't know. So we're not going to give you things that are insanely hard just to screw you up, because that then doesn't show me that what you know. Like if I'm testing long division, a problem like this actually is not bad because it makes me understand that you know to move things around. You know that you have to put the zeros in there. You know your steps. Now, if you didn't put the zero in there and you did your work, the rest of the work correctly, but you didn't put the zero, so that kind of messed you up, am I going to give you full credit? No. But am I going to give you no credit? No. I'm going to give you partial credit because you showed me you understood the main process of division. You made one little mistake there. Or like when I did the problem earlier and I said -8 is, or 0 is not greater than -8. It's like, if all your work's correct and that was the mistake you made, like I'll probably take off a point or two on that problem. It's like, it's not the end of the world because it's a little mistake. It was a lapse in error. So, but you had the rest of the work that it showed me it was correct. So, but yeah, it's my goal is to make sure you understand what we're doing, and that's where I'm looking in that respect. All right, so this is how you would type this answer in. Your quotient's there, your remainders above it. In the moment of truth, did I do it all correctly? Yes. You guys want to try one more long division problem before we go on to the other ones? Synthetic.
No.
Let's try. I'm going to give you guys an easier one to try, but I want you to try. Let's try one more of these. Oh, this is a good one, actually. Try this one. Nice thing is I've got 2 weeks to do chapter 4. So if it takes me a little longer today to get through something, it's fine. So for those of you who still work, if you look at, or for those of you who are done, you can look at the board and check your work. You can see this one was pretty straightforward. Everything was on order. There was nothing missing. So we get 3x squared plus 3x minus 6. And then there was a remainder of 1 at the end. We're going to come back to this problem actually in a minute. But I want to show you synthetic division first. All right. So synthetic division is one of those things that kind of breaks my rule of showing things that don't always work. But it's really important, and for the vast majority of problems, you're going to be using linear functions anyway and looking for factors. So synthetic division is a very nice, quick way to check things. Synthetic division, huh?
They're like the first one we did.
Similar. It's just with numbers, basically. A little simpler than that, though. Synthetic division is a simplified version of long division. It's you still have to do the work, but it just breaks things down a little bit simpler. To set up your synthetic division, you have an upside down L. The number that goes out in front is what would set that equal to 0. So in this case, I'm putting a 2 out in front. Okay, so that equals 0, so x equals 2. So the 2 goes out in front. Inside here, I'm putting my coefficients of those numbers, and I need them all. So in this case, I have 1, I have 0 for x squared, I have negative 11, and then I have 14. Okay, so you need every coefficient. So if there's a term missing, you have to put a 0. Okay, and the same concept as before, they have to be in order. Rewrite this because I want to get rid of it. All right, so first thing, anybody have any questions with how I set it up? Does that make sense, the process? Okay, because now we have to do the work. And that's a process in of itself. All right, so first number, just comes straight down. And then you're going to keep repeating multiply and subtract over and over again until you're done. So 2 times 1 is 2. Now subtract. 0 minus 2 is negative 2. Oh, sorry. You don't subtract yet. I knew I was going to screw that up. That's why I checked it. Just add down. So 0 plus 2 is 2. 2 times 2 is 4. Add negative 11 plus 4 is negative 7. All right, we changed the sign beforehand. 2 times negative 7, negative 14. Negative 14 minus 14 is 0. All right. So multiply, add, multiply, add, multiply, add, all the way to the end. Yeah, don't subtract. I missed it. Multiply, add, multiply, add. You change your sign in essence doing that. That's why the sign changed. So that's what takes care of the subtraction. Right? All right. Questions with that? Next step, we have to write our answer. My terms start off with x to the third. I go one less than that. So I have 1x squared plus 2x minus 7 with a remainder of 0. It's always one less exponent than you started with.
Yeah.
No, you wouldn't have a remainder. But I think the question they ask you for it, so. Huh? Oh, I'm going to do a few more of these. Don't worry. I'll do a few more of these. All right. Everybody got this down? Okay. So Alex actually sets it all up for you on the synthetic division topic. There's many other topics that we're going to do that use synthetic division that they don't set it up for you. That's why I wanted to explain to you how to set it up first. Okay. But the Alex stuff for synthetic division actually sets it up. So here's the problem completely set up for you. Notice how it is a -5 on the outside. We have the -1, -5, 0 for the x term, and 7 for the final one. And in Alex, all you're in essence doing is filling in boxes. But it's the exact same thing we just did. So, first one, bring down. So that's -1. Multiply. -5 times -1 is 5. Put the 5 there. Add. -5 plus 5 is 0. -5 times 0 is 0. 0 plus 0 is 0. -5 times 0 is 0.
Easiest
So-
one there is.
Yeah,
That or 1 times
7 plus 0 is 7. All right. I see the deer in the headlights. The zeros kind of make this, as funny as it sounds like this one. Oh, it's easy. It's all zeros. That's easy to confuse things, though. It's really quick to make mistakes. So you're always multiplying this and then putting it there. So -5 plus -1 is 5. And then you add always that. So -5 plus 5 is 0. And now we multiply again. Yeah, you always multiply times the bottom and then put it there and then add that. So 0, 0 plus 5, 0, 0, 0, 7 plus 0 is 7. So.
This is where the P and Q thing that I was talking about.
Oh, okay.
Find the 0. And what we find the 0. You have to find the 0 in the
Yes.
polynomial, and then you have to send that in the thing, and then you log the 0.
Yeah, this is nightmarish.
Oh, okay. I know what you're talking about. I'm actually going to make your life a little easier with that. I know what you're talking about now. It's the factor theorem. Yeah. Yeah, I know what you're talking about. All right. Now, so my quotient, remember, it's always one less exponent, right? So in this case, I start off with x to the third. So it's going to be -1 x squared. You do not have to put the 1. If you don't put the 1, it's fine. It'll still mark it right. And then I don't have to put the zeros, but I would have 0x and then 0. So I don't have to put them. If you put them, it's fine. It will not mark it wrong. So if you put 0x plus 0, it's fine. You don't have to. And then my remainder is the last number is 7. Correct. You can still have a remainder. And actually, that's an important concept in the next major theorem that we're going to talk about. So, all right. Go back to this problem. Is 3x minus 1 a linear factor? Okay, let me ask this question differently. What is a linear factor? Nope. Yes.
Slope doesn't change. Or
That's a very complicated definition of what a linear factor is. But yes, the slope doesn't change, but there's a way easier one. There's no exponents in it. Okay, linear means x, the highest degree is 1. So in this case, 3x minus 1 is a linear factor. It is 3x minus 1. There's no exponents. So I can do synthetic division with this problem. Remember, my goal is I have to get that to equal 0, right? And set it. So in this case, if I do 3x minus 1 equals 0, x equals 1/3. Okay, because I had the 1 divided by 3. So I can set up synthetic division with this problem and do it. So if I do 1/3 on the outside, 9, 6, negative 21. Let's see if we get the same thing. Bring down the 9. What's 9 times a third? 3. 6 plus 3? 9. 1/3 times 9 is 3. Negative 21 plus 3 is negative 18. 1/3 times negative 18, negative 6. And that ends up being a 1. So I would have 9x squared plus 9x minus 18 plus 1 over 3x minus 1. Are those two the same? It's just 3 times it. Okay. So either way, they would have factored out the same. The difference is the way that you set up the fraction in that respect. So 3x minus 1 is actually the same as x minus 1/3. But when you're dividing them, the 3 isn't in front. So it changes the quotient, those things a little bit, but it's still the same division. So while they look slightly different, it's off by a constant, which is fine. Okay. So you can do this problem either way and get the right answer. All right. So huh? No, that would be the final answer right there. That would be the final answer. Because actually, I did make one mistake. Because this would be x minus 1/3, not 3x minus 1. I did write that wrong. So if you were to change it back, it would have been 3 over 3x minus 1, and then you would be able to factor out the 3 out of the whole problem. And that's fine. So either one of those is the same thing. Okay. So anytime you have a linear function, you can do synthetic division. All right. Still have time. Now, the question is where are we going to start using this? There are a couple of theorems that we will use this for. So when we're looking at here, this is the remainder theorem. So the remainder theorem states if I divide it by a factor or a term, whatever the remainder is the same answer I would get if I plugged that number in for the problem. So they want to find P of 2. So if I did P of 2 is negative 2 to the 4th plus 2 times 2 to the 3rd minus 4 times 2 plus 5. Right? So I get negative 16 plus 16 minus 8 plus 5, which ends up giving me negative 50. Now, if I did synthetic division with this one, negative 1, 0, 0, negative 4, negative 3. Those come out to be the same answer. Always. The question is which one's faster? That depends on you. The concept of the remainder theorem equaling negative 3 honestly isn't as useful when like we're trying to find a value for a number. But what number would be? What's the numbers we're always trying to look for when we're doing these problems? The zeros. So if my remainder comes out to be 0, I now know that that is a factor of the problem, and I can remove it, and that's helpful. That means it's one of my zeros. It's one of the where it crosses the x-axis. Okay, and that's useful in being able to simplify down problems, which is where your P's and Q's come into play. Okay, so while this part right here, depending on how complicated this is here, this might actually be faster. Like I was able to actually do this a lot quicker than that and probably make less mistakes with your sum once you get better at doing synthetic division. So and you'll always get the answer will always come out to be the same. That's the concept of the remainder theorem. So the remainder theorem really leads into the factor theorem. But I want to show you because Alex wants you to do the synthetic division for this. So, oh yeah, sure, sorry. I'll go back.
Write it out.
Yes, which is exactly what I'm going to have to write in a second. So you're one step ahead of me. All right, so when we're looking at this now, Alex wants to make sure that you've done the synthetic division. So it asks you for the quotient and the remainder, where typically when you're doing the remainder theorem, you wouldn't need that information. So when you're writing this out, the quotient, exactly what you just said, it'd be negative x to the 3rd It's plus 4, minus 4. Minus 4. Minus 4. And then my remainder was negative 3. And then p to the second, or p 2 is negative 3. So you'd write that in like that. Okay. Yeah. Okay. So now the factor theorem states that if the number you plug in gives you 0, then that linear function or linear divisor is a factor of the problem. So in this case, we want to determine if that's a factor. So we're going to do synthetic division, and if the remainder comes out to be 0, it's good. If the remainder comes out to be something other than 0, it's not. So we have the so that I'm going to plug in 2 for this. So I have the 2 on the outside. And then we have 2, negative 1, 0, 3, and negative 9. So bring down the 2, 4, 3, 6, 6, 12, 15, 30. So 21 is my remainder. So not a factor. And P of 2 equals 21.
I remember learning, a professor taught us, literally, you could put that function into the graphing calculator, and you could find your zeros.
Yes. So you absolutely can. You could just type the things in the calculator, and if it crosses the x-axis at that point, it is a factor. Problem is that that only works well if they're whole numbers. When they are not whole numbers, it becomes a little more complicated. So I think let's check the next topic on this. I'm gonna jump, but that's okay. All right, see if x minus 3 is a factor of this one. All right. So we know x minus 3 is a factor, which means that x equals 3 is a 0. Okay. So x equals 3 is 0. Hold on, let me get the exact name of it. The rational zeros theorem, which is your P's and Q's, states that all factors of it will come down to the factors of the constant and leading coefficients divided by each other. And you get this massively long list of factors. Okay. So this is the P's and Q's that everybody hates. And I'm going to show you a shortcut to it. Because the point of the rational, so a ton of math that you learned today was designed in an age where you didn't have graphing calculators and you didn't have calculators. Okay. We have them. And we should be able to use them. And that I don't have a problem with. There's certain things that when I show you it and I expect it done a certain way, it's because later on, those things come up and you can't use the calculator to be able to do that part out. Or there's a reason where the calculator is not necessarily going to give you all the information you're going to need. Okay? So understanding how to do different methods is helpful. I am not going to have you ever do out the rational zero theorem and find all my rational numbers that direction. Okay? I'm not going to have you do that because there is no math after this point where that is useful. Okay? It is one of those artifacts of a previous time. There is a topic, and Alex would ask you to write them out. So I'm going to show you how to write them out, but we're not going to find them this way. Okay. So to write them out, it's quite simple. All we're going to do is we're going to take this is my P, and the number in front here is my Q. So the factors of P in this case are 1, 2, 3, 4, 6, and 12. Yeah, and positives and negatives of all of them, yes. This is why I don't write the positive or negative, because you're literally just going to rewrite them all anyway. Yeah. And Alex has the button for plus or minus, so you don't necessarily have to rewrite them twice. And Q, since Q is in this case is 1, makes my life a little bit easier. So my factors of this one would be 1. So basically it's just the top 1, 2, and it's plus or minus each one. Huh? And Q is 1. So every one of those would be divided by 1. If Q was, say, 2, I'd have every one of them divided by 1 and every one of them divided by 2. So you have to basically have fractions on them. The reason why I use this, and the reason why this piece is kind of important, is because let's look at the graph of this function. Hold on, because I have a different graph in here, so I'm going to type this right. All right. So when we're looking at the graph, so here's my graph. Typically, your graph will go from negative 10 to 10. Okay? In this problem, I know I can have rational numbers from negative 12 to 12. Okay? So I want to make sure my graph looks at least that range, or at least that domain. So this way I don't miss anything coming back down that I might have. All right. So the rational value theorem will help you make sure you understand what domain you're going to look at your function on. Okay. In this case, it seems to cross twice. And we already found that one, right? We found the 3. And it also seems to cross at -1. Okay? This is where that synthetic division comes into play. Because we can find our rational zeros. But what happens if we make the next step and say, I want you to find me all of my zeros? We can have zeros that don't exist. We can have complex numbers and imaginary numbers. Or if I want you to completely factor out the function. Okay? This is where this graph is going to help you do that and with synthetic division. So let's go back to my original problem that I have here. We know that x minus 3 is a factor. I'll duplicate this so I don't lose that P's and Q's. We now have a simpler function here. Okay, this right now is x to the third plus x squared plus 4x plus 4, right? I can do synthetic division again on that using my -1 that I just found on my graph. So I can do -1 and use the 1, 1, 4, 4. Bring down the 1, -1, 0, 0, 4, -4, 0. So -1 is also a factor, right? By doing synthetic division, I have verified that. Okay? The graph verified it for me, but now we've algebraically verified it. And now I have this function here. That's x squared plus 4. So what I've now done I factored my problem. Okay. Using synthetic division and the graph, I've now completely factored my problem. And with it being factored, I can find all of my zeros, including the x squared plus 4, which is plus or minus the square root of 2i. Or no, plus or minus 2i, sorry, not the square root of 2i, plus or minus 2i. So I would get my complex factors in there as well. This is why I don't want you just using a graph completely on its own, because sometimes the values don't come out to be exact. They're going to be fractional answers in there. The nice thing is if they are a fractional answer, you'll get about what it is, so you can then go through and test it out and pull that information out of the problem. So it helps you to a point, but doing this piece completes that part. Okay, yes?
So are you gonna ask us on a test about P and Q?
No, I will not have that question, that topic will not be on the test. I will have questions on the test where you have to completely factor a problem, or that you have to find if something is a factor of the problem. Those will be on there. But no, I won't have you just do one with P's and Q's. Because like I said, it's more of a nice thing to use to help find your graph more than actually solving problems that way. Yes. You could use your rational value, the P's and Q's. So you know that -1 is a possible value. You would literally just go through and test them all. That's what they were annoyed with, because their teacher previously had them test all the values. So yeah, in essence, what you'd have to do if you didn't have a graph at some point in the past, they would literally have gone through and plugged every one of these into synthetic division and found it. Now, how many factors could I possibly have for this? So the most I could have is 4, right? So here's, in essence, what they would do is they would test something. So they would, and they most likely would have started off with 1. They'd have tested the positive 1 and the negative 1. Negative 1 would have worked. Okay? No. Well, yeah, negative 1. Negative 1 would have worked. So negative 1 would have worked. They would have then had a smaller problem to work with. They would have then tested another number on that one. So they would have worked their way down basically to get what we did here, the complete factorization. So they would have pulled out the negative 1. They would have found the 3, pulled that one out. They wouldn't have had to test the 4, 6, those numbers, because they were already, at that point, they'd gotten down to a simplified problem that they know they could factor or can't factor. So normally, once you can get down to a quadratic, you don't necessarily have to do the rational value because you can factor it normally. It's the other polynomials that makes it really hard to factor, and that's where this stuff comes into play. So, and it would work for any of them. If I gave you x to the 10th and worked on it, you'd have to, it'd take you a lot more steps, but you could technically keep working your way down. No, I'm not giving you 1x to the 10th on the 10th. So, does that make sense? All right. Did that.
You said it won't show up in higher math.
So the rational zero theorem, just in essence, as the rational zero theorem, does not. Knowing how to factor a problem out like that absolutely does. Being able to break down a problem into its linear fractions or as simplified as you possibly can absolutely comes up more. When you're looking at partial fractions and stuff in Calc 2, when you're looking at breaking things down in Calc 1 for differentiation, those things definitely come into play. So knowing how to factor any polynomial is important. All right, so that I'm just going through and seeing which ones. Yeah, that one little thing I just did there kind of covered a ton of them. Let's do this one real quick, and then we'll be done. All right. All right, so this is the function below has at least one rational zero. Use this fact to find all zeros of the function. All right, so step 1. Just look at the number there, because that's the one that's the p. That's the one on top, right? So the biggest and smallest factors of that is going to be plus or minus 10. Correct? So on my graph, I only need to make it look between plus or minus 10. So here's my graph. Okay? So step 1, look at the very last number that's p, and that's going to give you the maximum domain that you're going to have to look at in the graph for rational functions, for rational zeros. So it looks like it crosses 4 times. So let's click them. All right, those are fractions. Those aren't going to be very helpful to me. Those are not. Those are going to be helpful to me. Okay? So I know right now that 2 and 5 are both factors. Correct? Yes.
Does it matter which one you use?
You're going to do them both, actually.
All right.
And it does not matter the order you do them. All right? So I know 2 and 5 are going to work. The other 2 are fractions. I'm going to have to do a little more work to figure those out. But we know 2 and 5. So I'm going to do the 2 and the 5. Oh, please tell me he didn't have you do long division for every one of them.
Yeah.
Oh my God. Yeah, these you can always use synthetic division because you're pulling out a linear factor. So always use synthetic division for this. So we're using, what was it, 2 and 5? Yeah. All right. So we'll do the 2 first. I want to do 2. It doesn't matter which one you do first. 7, negative 50, 76, negative 3, and negative 10. 7, negative 36, 4, 5, 0. Now, your remainder should always come out to be what? 0. If it doesn't come out to be 0, you screwed something up. And since you know it's supposed to be 0 on the graph, go back and check your math here. Because that's important, because now I'm going to actually use these numbers right there. I'm not even going to like work it out into the function. I'm just going to pull them directly into my next synthetic division. So my next synthetic division is going to be 5 and 7, negative 36, 4, and 5. So 7, 35, negative 1, negative 5, negative 1, negative 5, 0. So now, that right there, I've taken this problem and I factored it. I have x minus 2, x minus 5, and then 7x squared minus x minus 1. Okay? All right. Now we're down to a quadratic, correct? There's 2 methods you can do this to do this. You can factor it, or just use the quadratic formula. You can't factor this one, not easily. So let's just go to the quadratic formula for it. So good practice of the quadratic formula that we haven't actually done yet. All right, so A is 7, B is negative 1, C is negative 1, right? Okay. That's quadratic formula, correct? Okay. I do not know how any of your teachers taught you how to do this before. Do not plug all the numbers in the quadratic formula. Do your discriminant first. Okay? The discriminant's the piece under the square root. Always do that first. Because, 1, it's going to tell you if there actually is any numbers, because if it comes to be a negative number, there is no real zeros. Okay? Second is you then can simplify it on your square root, so you don't have this massive problem to deal with. So let's just do the b squared minus 4ac first. There's no real zeros. It'd be negative. It'd be imaginary numbers at that place. So we got negative 1 squared minus 4 times 7 times negative 1. So 1 plus 28 is 29. Can I simplify the square root of 29? No. So my quadratic formula now is negative 1 plus or minus the square root of 29 over 2 times negative 1. Oh, 2 times 7, sorry. Yeah. Which I'm going to do here anyway. And there's my answer. A little simpler than writing out the entire quadratic formula and simplifying it down step by step by step. Okay? Those are my other two zeros. So I've got 2, 5, and 1 plus the square root of 29 over 14, and 1 minus the square root of 29 over 14. Those are my 4 zeros. So you can see how I'm using a combination of the graph, synthetic division, to break things down, and then using the methods that I know about quadratics to find the rest of the answers. Okay? And those are all the 4 exact zeros. Where if you just use the graph, you're going to get two estimations. You wouldn't get the exact values. And the exact values are important. Questions with that? Okay. We will continue from here on Thursday.